Okay, so yeah, hello and welcome to this session. So yeah, we're going to be looking at kind of going from the start, kind of complete no knowledge, using this language called R to try and predict the outcome of a football match. So we're going to use historic data on kind of previous year's games, and then use that to try and predict the outcome of a new match we haven't seen yet. And so I posted a link right at the top of the chat here. I think I'll repost it just so it's at the bottom of the chat. And this is kind of the main link that you want to go to kind of get all these resources. So if you follow that link, it will open up a page like this. And if you scroll down a bit, there's a few links on here, just some useful resources. And the main one we're going to need is this help guide. And then also the recording is going to be put here once the session is finished. So if you follow the link in the chat, open this up, and then go to the help guide and open that up there. And so that's going to open this document here. This is going to be the thing we're going to work through in the main session. And then we're going to move into breakout rooms to kind of actually work through how we would do this prediction thing, kind of making the solution for ourselves, kind of filling in some blanks. And we'll do that in a different notebook. So we're going to work through this here, and this is the final product that we're aiming for. We want to be able to take, we're going to focus on the Premier League just to keep things simple, and we're going to take any two teams, and we're going to have one being the home team, one being the away, and then we want to be able to predict what the probability of any particular score is. So here, this was after the model was completely trained, and we had Manchester United at home playing Stoke City away. And it predicted that there's a 15% chance of a 2-0 victory, 14% chance of 1-0, and the chances of Stoke winning were fairly slim, but not impossible. So we want to be able to do this for any team, and hopefully with code that's general enough that we could also apply it to any league and any kind of span of data. So we're going to be using a language called R to do this. So I'm first going to introduce what is R, what's this thing called RStudio, and this thing called RStudio Cloud, which we're going to use to actually do our coding. So R is a statistical programming language. It was made, it's quite an old one now, perhaps in the 80s. And it was based on a language before that called S. And so it's mainly made for statistics and for graphics visualization, but it's kind of grown a lot beyond that in the past few decades. So now really R can be used for literally anything. You can do kind of advanced machine learning, big data applications, natural language processing. You can make a website with R. You can write a book with it. Like, there really is no limits to what you can do. But R itself is just a language that you can code in and get outputs. And so we can use this language directly, but it's a bit of a fuss. It's nice to have an editor that we can do stuff in that's a bit more convenient. And so that's where RStudio comes in. So RStudio is what is known as an IDE, which stands for an integrated development environment, basically a fancy text editor. So it's a place that we can write code and run the code, and it's kind of got a load of nice kind of convenience features to make it easy to do that. And so, I think my R installation on Windows is broken, so I might not be able to show you this. That doesn't matter too much because we're going to use something called RStudio Cloud. If you've taken our R course over summer, you might be more kind of comfortable using RStudio on your local computer. If you are, you're free to do that. But if you're kind of unsure on any of that, RStudio Cloud is the easiest way to do this. So yeah, it doesn't look like that's opening for me. We'll carry on with RStudio Cloud. So what RStudio Cloud is, it's basically an installation of RStudio on the cloud. And so you can use this for free. And it allows you to do coding in R without installing anything, without having to kind of set anything up on your own computer. You just have to follow this link here to go to RStudio Cloud. And so if you've not made an account, you'll have to make an account. It's free to do so. And then you can sign into that. And you'll end up with something like this, although yours will be blank here. And so what RStudio Cloud does is gives you, for free, every month, 15 hours of time to run code. And so after that point, you're not going to get charged, it'll cut you off. But if you're doing more than 15 hours a month, well, it's probably time to actually get RStudio set up on your own computer. If you are interested in doing that, in this kind of introductory page here, we have a link to the instructions that that we have in our beginners course on how to set up RStudio by yourself. But anyway, so yeah, we're going to use this thing called RStudio. So when we get into RStudio, it's going to look something, so RStudio Cloud, it's going to look something like this, but with no project here. I've already started a project off already. And so what we're going to want to do is create a new project. But we're going to do that by using this drop down here. So don't click new project itself, but we're going to do new project from Git repository. And so we're not going to get into what a Git repository is. It's basically just a place that you can store code. And so rather than doing something completely from scratch, we're going to give you some foundations to work from. And so if you go back into this this help file here, so it has these instructions here. So the new project drop down, new project from Git repository, and then just copy this link below here. And this is a link to the repository where all of the code is stored. So if I go into RStudio Cloud and I copied that in, I then press OK, and that would create me an environment that has all of the code that we're going to be using already in it. So I've actually done this earlier in Blue Peter style, and you'll end up with something like this. It might take a while to boot up. These aren't the fastest of servers, but they're free, so you can't complain. And so once you've got to that point, well, yeah, we'll give it a second to boot up. I'll just mention it in the meantime. If there are any questions at any point, the chat is the best place to ask those. So we have three mentors here who are kind of on hand to answer any questions. If things aren't working, if you want clarification on an idea, just pop it in the chat and they'll be able to help you. So this will have loaded up, and it will probably look something like this. Okay, so this is probably how it will look when you first start it off. So you've got this kind of big window on the left here, and there's some other ones here. But don't worry about how everything is laid out. In fact, I'm going to change my layout in a moment, just because I prefer it in a different way. But the important thing is that you have all these different panels here, and so yours might be in different places, but you'll have the same ones. And so there's one panel for, let's say, files here. That could be anywhere. Just click on it if you want to get to it. Okay, so let's kind of move on from there. So yeah, the first thing we're going to do is we need to run a command to install all the add-ons that we're using for this project. So we'll get more into what that means in a second. But for now, there's just one line of code here, and you can copy it from the help guide. So it's renv : restore with the brackets on the end. And you're going to take that and put that into the console. So actually, let me zoom in a bit so all this is a bit larger. There we go. Can't hide that. Anyway, so you go to where it says console. If that one isn't selected, then you would... Oh yeah, so yeah, you don't need to be... Okay, yeah, you should be following along with these first bits. Once we get into the actual coding, you don't need to be following along. But this is setup stuff, so you can follow along now, or, if you'd rather just sit back and wait, then when we get to the breakout room, you can set it up then. But anyway, yeah, so once you're into RStudio Cloud, take this command here, renv restore, and just copy that into the console and press enter. So I've already set this up, so it's not going to say, it's not going to do anything, but for you, it's going to list out a load of things and then give you an option y/n, which means kind of yes or no. You just put a y for yes and then press enter. And that's going to take a bit of time installing all the things that you need to do to get set up. If any issues happen with that, don't worry about it, and we'll sort that out in the breakout room. So for now, just get that running. It can take a bit of time to do, but if there's any difficulties, don't worry about it. Okay, so once you've got all this stuff loaded, in your files pane, you'll have a load of files. And these are kind of the templates and the guides that we've created for this workshop to kind of get you started. And so the most important ones are inside of this notebooks folder here. And so if we go on notebooks, we can open that up. And then the one we're going to be using for now is the help guide. And so there's different types of files here. The ones we're interested in are the .rmd ones. So we're going to open helpguide.rmd. And so from this point onwards, you don't need to follow along with any of the code that I'm doing. You just need to kind of watch, and then when we get to the breakout room, that's your chance to actually apply some of this stuff. So this is actually the same help file that we had here, but this one is interactive. So yeah, so we set that all up, and then we opened a notebook. Okay. So the first thing we're going to look at is how do we run code inside of this document. So an R notebook, which is what this document here is. So it's kind of a notebook for writing your R code. Is made up of these things called code chunks. A chunk is basically a block of code, and we can surround these chunks with text. And so to create a chunk, we use this insert button at the top, and we're going to insert an R chunk. So you can actually see here that RStudio can deal with many different languages. It can use kind of Python and Bash, but we're going to be using R for this session. So we're going to go on insert and R, and that gives us a new code chunk. So a code chunk is these 3 backticks, the language we're using, and then some backticks. And then inside of here, we can write in some code. Actually, I'll mention quickly, if you want a shortcut for doing that, Control Shift and I will do that. So if I do Control Shift I, oh no, wait, is it Control Alt and I? Okay, so I think I got the command wrong there. Yeah, okay, so don't use the shortcut at all. It's Control Alt and I. Anyway, so from in here, we can write code and then use this play button to run it. So we're going to start with this line of code here. We're not going to worry about what it means, but this is an example of some code that we can run in R. It turns out that it's the code to output the words hello world, which is like the canonical first thing you do when coding. And so we click the play button to run it. I got an error there, but I think it's worked anyway. So if you get an error, yeah, I just closed that. It seems to be working fine. So that printed out hello world is the output. So the play button there, that's to run it. You can also use Control Shift and Enter to run one without clicking the play button. So it might be the case that our code is taking a really long time to run, or it gets stuck in an infinite loop. So I'm going to create some code here, which is going to create an infinite loop. Let's not worry about what it does, just this is going to run forever. So if I run this, it's never going to finish. It's going to keep buffering. Basically, I'm saying, yeah, just keep running forever. So I can stop code from running, either if it's taking too long or it's stuck, by just clicking this square here, the stop button. So I click that, and that will stop the code from running. But let's put this back to how it was before. So when it's working well, it just plays, and there's no option to stop because it's finished. Okay, and so another thing to mention is that R generally doesn't care about spaces, new lines, or indentation. So if I take this code block from up here, and I put some spaces in here, put a new line there, maybe indent this a bit, R doesn't care. This is the exact same code as it was before. But we tend to put in certain patterns of spaces and new lines indentation to make it easier for a human to read it. But what is important though is that R is case sensitive. If I change this to print with a capital P, that's no longer going to work. It has to be the exact correct case. Okay, and so if we start any line with a hashtag, or actually anything following a hashtag, that's not going to be run. So if I put, say, a hashtag here, and then follow it by some absolute garbage, this clearly isn't a real command in the R language. If I run this, no problem, because the hashtag means anything after this, ignore this. This is just here for the user's sake. So you often use these for kind of giving some instructions or kind of explanations of what's happening. So this prints out hello world. You do something like that to kind of say what the code is doing. And so this is relevant for the actual template that we're going to be filling in. So inside of this notebooks folder, there are 2 other files of interest. There is template empty and template complete. So we want the RMD ones. And so template empty is the one we're going to be filling in, and template complete is the final solutions you can look at if you're stuck at all. So let's have a look at the empty template. It looks something like this. And so inside of here, there's going to be certain lines that have a comment line starting with a hashtag, and then a to-do. So this is something that we're going to need to do to make our code work. And so here it says our to-do is to import the package ggplot2 for the purpose of visualization. So we'll explain what that means in a second, but we would complete that task by removing this this following line. So this here is kind of a placeholder saying, hey, this is about how long your code has to be. So we would delete that and replace it with whatever the correct code was there. So those are the to-dos. There's also these things called checkpoints, which I've thrown in. So these are optional steps. Your code will work just the same. You'll get the same answer if you don't fill these in. But they're very useful for kind of making sure we understand what our data looks like and that you're kind of, you understand where you are. So you could just kind of add a new line under this and kind of put in whatever code you wanted and run it. But you could miss these out and the code will work just fine. Whereas the to-dos, you're going to have to do those or the code's not going to work together. Okay, so that's all of that. Okay, so let's start by explaining about these things called imports. So, R is what's called an open source language, and that means that anyone can contribute to it, can kind of add features to it. You're not waiting for a single company to decide what should and shouldn't be in the language. And that's quite a beautiful system because you're no longer limited by one company's time and resources. If you want to have, if you want to do some kind of advanced geographic spatial stuff, like someone else, as long as someone else is interested in that, they've probably done it for you already, and you can use that code to kind of get a head start on things. And so the way we kind of use these kind of add-on packages is to use this command called library. And so what library does is it loads up packages that you've installed. So when we did that renv : and restore, that was installing a load of packages that I predefined that you're going to need for this. So that's kind of installing them, and then to load them up, we use library, and then we put the name of the package inside of here. So here we're loading a package called dplyr, which is used for kind of manipulating and transforming data sets. And then whenever we import something, we typically follow it by a comment saying kind of what's the reason we've imported this. In this case, it's for data manipulation. And there are a crazy number of packages. So there's this website called CRAN, which is the, what does it stand for? Central R something, whatever. Central Repository for whatever. Comprehensive, yeah. Brilliant, yeah. And so, yeah, this is a website that contains, not sure how I hide this thing at the top, but anyway. There we go. So it's a website that contains a load of packages, kind of extensions for R. So if I go on packages here and then list them all by name, there are a lot. I'm not even sure what the number is, but there are a crazy amount on here. And actually, this isn't even a comprehensive list. Like a lot of packages aren't even found on CRAN. You can find them in other places. But really, like whatever you want to do, there's going to be something for that. So I guess if I wanted data on basketball, I spelled it correctly. There's 5 different packages related to basketball. So this one for analysing basketball data, another one for analysing basketball data, basketball data analysis, pretty much anything. I think there's even a package for making memes. Crazy amount of stuff on there. And that's the beauty of using a language like R. So yeah, that's what we're doing at the start, just importing those other toolkits, like why reinvent the wheel? Let's use code that someone else has made. Okay, so we saw earlier how we can get R to output some code using print, but that's very much in the here and now. Like what we would really like to do is to tell R, hey, remember this thing, we'll get back to this later. And we can do that using a thing called variables. So variables are a way of giving R memory for storing a value for later use. So the format for assigning a value to a variable is this. So we take some value and then we use a less than sign and a hyphen to make this left arrow here. And then we put a name of a variable on the left here. So what this is saying is take this value and store it in this name. And now whenever R sees this name in the future, it's going to go, oh yeah, I remember you setting that to be the value of that. And so I will replace it with the value you set it to. And so an important thing to note is that variable names in R cannot contain spaces. So instead we use underscores or hyphens or periods as a replacement for those. And so once we've created a variable in R, R will remember that value until we close the window. And it will also, so that's fine. So here we create a variable called players, and we're going to give it the value of 11. So starting off with 11 players. If I now do print and players, R is going to go, oh yeah, I remember you setting players to be 11. I'll replace that with 11. But we don't have to do that manually. If I just run this, R will go, oh yeah, this was a value of 11, and then we print out the number 11. I can also reassign it, give it a new value, And so now we're saying, forget the old one, players now has a value of 10. And so if we do that now, then if we print this out, we get a value of 10 here. Now, it's important to be wary because RStudio allows us to run cells or chunks in any order. So actually, I can go back to this players is 11, run this, and then run out print at the bottom here. And this now has a value of 11, even though this 10 one appears after it. So the order that things appear on the page make no difference. It's the order that you run things in that matters. And so generally I would advise only running things from top to bottom. And if you ever want to kind of run everything above where you are, you can click this button here. That's going to run everything above to kind of get you back to the correct state before this cell. There's also a lot of options in this run drop down here that you can use for kind of various different ways of running things. There's one final thing to mention on variables is that if we ever have any like high level parameters that control how the whole notebook or script behaves, then we often denote these with all caps. And that's kind of to signify these are important values that don't change throughout the code. Okay, and so there are different types of variables. So we can have variables for text data, for numbers, for kind of logical true-false values. But when we're using text data, we have to explicitly tell R, hey, this is text here. And we do that by using either single or double quotes. And you can use either, they mean exactly the same in R. And so we do this just to let R know, hey, this is text and not a variable. So for example, we can create a variable called greeting with the value of hello in single quotes. So now greeting contains the text hello, and we print that out. So if we run this here, we get hello printed out. We could also have used double quotes, means exactly the same. But if we try and do this without using any quotes, then R's going to look at this and go, okay, well, you didn't put quotes here, so clearly it's not text data, and so it must be a variable. And it tries to remember, well, what value did you set hello to be? And it can't find one. So, object hello wasn't found. I can't remember what value you set this to. And so we just get an error here. We should have used quotes. Okay, so one more thing we're going to touch on is these things called functions. So functions are the way of getting R to do something. And so they have a syntax that looks something like this. So there's a name of the function, and then brackets, and then inside these brackets we put different inputs. We separate these all by commas. There could be no inputs, there could be one, there could be two, there could be an infinite amount. And we just apply those all in there, separated by commas. So these are kind of the values that we put into this function to control how it behaves. And so some functions will return a value, and in that case we can take their return value and assign it to a variable to kind of store for later. So here we could run a function, perhaps this returns a number. We could then save that number using a left arrow assignment into some named variable. Then we could use variable in our code to refer to whatever value this returned. And so one more thing about functions, that some inputs have names to them. So the syntax for doing this is that unnamed ones, we just put in just the value here. But named ones, we put the name equal to a certain value. So you might see this at some places in the code. And so the last fundamental we're going to look at before getting on to some of the actual kind of useful stuff is these things called data frames. So data frames are kind of a really pivotal part of the programming language R. And they're used for storing kind of tabular data, so columns of data and kind of multiple rows of values of those columns. And so another thing in the R language is these things called tibbles. And so tibbles and data frames are basically the same things, but tibbles have a few special properties that make them print out, so kind of output to us in a prettier way. So I might use the word tibble and data frame interchangeably. They mean the same thing, but tibbles tend to be prettier. And so there are a few ways that we can kind of get some information out of a data frame. And so at this point, I'm just going to move around my panes so I can have the notebook next to... Actually, no. I'm going to do everything in the notebook. That will be clearer. So I'm going to create a code block here. So I'm going to use, insert and then R. And so one dataset that comes built in with R is this MPG dataset, which stands for mile per gallon. And so if I print this out, I get something like this, just information on different cars. So there are a few kind of functions that I can use to get some information about this. So one is head, and that's just going to give the first few rows of a data set. So here it gives the first 6 rows. So just kind of the start of it, head for top. If I wanted the bottom few rows, I would use tail, obviously tails at the bottom. Another thing I can do is ask how many rows there are. So I use n row for that. And here there are 234. I can use n col for how many columns there are. And that is, there we go, 11. And so some other ones to use, there is str for the structure of a data frame. Sorry, I missed out the brackets here. So that won't change on yours, but yeah. If we just do str and then brackets, that gives the structure of a data frame. So it's going to have kind of what different columns we have. What's it doing in there? That should be closing or whatever. So it has what columns we have, what kind of type of data is in those, and some of the values. And then there's a few other things that we can see. So summary for kind of numeric summaries and names for what the names of the columns are. So you can have a play with those in the breakout room. And so we can read a data frame into R using this read.csv function. And then this is going to make a data frame. We can convert that into a tibble so it prints out in a nicer way just by putting that inside of tibble. But that code is given to you, so don't worry about that. Okay, so the last thing I'm going to talk about before we get into the breakout room is this thing called the tidyverse. So the tidyverse is a collection of packages that are used for data science and data analysis. And the important part of the tidyverse is that they work really well together. So whereas in some languages like Julia or Python, there's loads of different tools that don't really gel together, the tidyverse is made to be very consistent, and everything kind of flows very nicely between each other. And this is all because they share this same consistent philosophy of how data should be treated. It's also a very intuitive and powerful way of dealing with data. And so the tidyverse has many different packages, and each of these packages has their own function. And so one of these is for data manipulation. And the name of the package inside the tidyverse that does that is called dplyr. So think of like pliers, for kind of, the tool for kind of manipulating things, and then D for data. And so dplyr has 5 main commands, and these are known as the dplyr verbs. We're not going to go into all of those. We're going to kind of offer a few important ones that are quite useful. So the first one is this thing called select. And so select is used for picking out certain columns from a data set. We might have a data set with 1 million columns. We just want a few of those. Then we use select to pick those out. So here we had the mile per gallon data set. Looks something like this. So it's got columns, manufacturer, model, decimals for engine size, a few other things there. And we might want to pick out just a few of those. So here we use select. You put the data frame as the first argument, and then we put the 2 columns we want to pull out here. So highway mileage and city mileage. And then we use the names that appear in the original data set. And that's going to give us just those 2 columns there. So that's how we use select. We can also use select to rename columns. And so what we can do, rather than just saying we want these columns, we set the new name equal to the old name. So here we're saying give me highway, city, and class, but rename CTY to city and HWY to highway. And so we end up with that in the final thing. Okay, so that is selecting things. Another part of dplyr is this thing called mutate. And we use this for creating new columns based on existing columns. And so we start, so it's the same kind of syntax for all these. We start with the data frame. Here we have a data set called presidential. And it has the terms of different presidents throughout US history. And so what we might want to do, we have the start date and the end date. We want to know, well, how long were they in office for? And so we would do that by using mutate, passing the data frame as the first argument. And then we do some sort of kind of calculation with our columns. So here we did end minus the start. And then we set that equal to a new column. Here we're calling it term length. And so that creates a new column at the end called term length, given the value of whatever formula we put in here. And so we see that there was different lengths in days of how long people were presidents. And so we can also use mutate to add a column with a single value, so the same value for every single row. And to do that, we just create a new column and just set it equal to just a single value. Rather than using like a formula here, we just put in a single value. Okay, and so the last thing that ties kind of all dplyr together is this thing called the pipe. And so the pipe is this symbol here, so percentage, right arrow, or I guess greater than sign percentage. And it's used for controlling how our data flows. So what the pipe does is it takes the output from the last thing we ran and passes it into the first input of the next thing we're running. And so we can use this to create a chain or a pipeline of kind of our data processing. And so there's an example below here. It's going to use some stuff that we haven't seen yet. Let's not worry about it. You'll learn more in the breakout room. But the important thing is we take this MPG dataset and then we pipe it into this function called filter. So filter is another dplyr thing. And as with all dplyr things, the first input is the dataset. But here, rather than putting this as the first input, by using this pipe, this is going to kind of automatically put it as the first thing and push this along to be the second input. We then take the output of that and then pipe that into the mutate function. So normally, we'd have to kind of give this output a name and then put that as the first input. But instead, we just pipe that, take the output of that, and put it as the first thing here, and then shuffle along that next thing to be the second input. And then we carry on with that, creating this kind of quite beautiful pipeline of data. So take the data, filter so that the year is 1999, add a new column, which is the highway mileage in kilometers per gallon, group by all of the classes, the different types of cars, and then summarize to find the average highway mileage for each of those groups. And that gives us something like this. So for every type of car, what's the average highway mileage? And I mean, this might seem a bit kind of difficult to read if you're new to R, but once you get a bit used to it, actually this is pretty much English. Like we read out what we do here, so it's a very nice way of coding. So yeah, so we see summarize here. What summarize does is it collapses down a data set into kind of summary statistics, but we'll see more about that in the breakout sessions. So the very last thing I'm going to talk about is this thing called ggplot. So visualization in the tidyverse is handled by this package called ggplot2. And so the GG in this stands for Layered Grammar of Graphics. It's based on kind of a design research paper a few decades ago. And so the philosophy behind ggplot is that you create a graphic by stacking layers. So we start with a base layer, then we add what's called a geometry. I'll explain that in a second. Then we could add kind of what scales our axes have. We could add axis labels, we could add theming, we could add a new coordinate system. And we do all these by separating the layers with a plus symbol. So we add these layers together. And so the most peculiar thing that we covered in that list there is a thing called a geometry. So all a geometry is kind of a physical element of the plot. It's kind of an actual visual thing you can see used to represent data. So this could be points, it could be text, could be lines, could be bars, could be an entire box plot. It's something to represent data visually. And so kind of the format of geometries is geom underscore and then whatever sort of geometry we're using. So it could be geom underscore text, geom underscore line, various things like that. But we'll see some kind of guided examples of that in the breakout session. So yeah, geom line, geom text, those are all examples. And so any kind of visual aspect of a geometry is called an aesthetic. So that could be the X and Y positions, could be the color, could be the size, transparency, the shape, anything that kind of describes how our geometry looks, that's called an aesthetic. And so inside of ggplot, we map variables in our dataset to aesthetics. So we're kind of saying this column in our dataset, that's going to be represented by, or that's going to represent this aesthetic, this kind of visual aspect of the plot. And we do all of this inside of this function called AES, which is short for aesthetic. And we literally just do kind of a mapping here. We'll see an example in it in a second. And so if we set any aesthetics in the base layer, that's the first layer, those will apply to all geometries. If you set them in a certain geometry, it will only apply to that one. And so here's a very comprehensive example of what ggplot can do. But you'll see some examples actually in the breakout session kind of explaining it a bit more. So here we take the mile per gallon data set and we just kind of put that as the first argument of ggplot, kind of pipe that in. And then we put in these are static. So we're saying take highway mileage and then map that to the x coordinate and city mileage to the y coordinate. And that's going to apply to every single geometry because we did it in the base layer here. So the base layer is this ggplot layer. We then add geometries. The points, we're going to use an added aesthetic of mapping engine size, that's disple, to the size of points. And then we're going to add a smooth curve. And here we don't use any aesthetics. Instead, we just manually set values. And when we're manually setting values, we don't use this AES function. We then add some labels, so saying my x-axis should be called this, y is this. And finally, I set the color of the grid to be dark blue. So don't worry about all this. We'll see examples of this in the breakout session. But with just a few lines of code there, we get quite a pretty plot of kind of highway mileage and city mileage, where the size is determined by the engine size. Okay, so that's all that I've got to share for this first part of it. So we're now going to go into breakout rooms, and we're probably going to stay in there until 5 o'clock. So once you're in there, you can have a look through the help guide again if you want, or you can open the empty template and start filling this out. So start kind of removing these blanks and filling them in. So we have 4 mentors here and 4 breakout rooms. So you can get to these by, I'll show you. So if you go into Teams, and if you go into the breakout room channel, there are 4 breakout rooms here. So the way we're probably going to structure these is that we'll use breakout rooms 1 and 2 for people that aren't very familiar with R, and 3 and 4 for people that have a bit of practice already. And so if you're not that familiar, go in 1 and 2. If you are more familiar, go in 3 and 4. Actually, looking at the numbers, let's actually just use 1 and 2. So 1 if you're not that familiar, 2 if you are more familiar. And Tim, which is me, and Martin, we'll kind of take 2 off ours. So I'll go in 1 and Martin can go in 2. So just use 1 and 2. So 1 if you're not that confident, 2 if you have a bit more experience. So you can go and join these. You don't have to leave this call. If you join a new call, it'll just put you on hold in this one. And at 5 o'clock, we'll join back in to kind of finish off the teaching part of this. Okay, so see you all in the breakout sessions. Okay, so we're now going to talk about the second part of this, which is actually like modeling the data. So far, we've imported the data, kind of transformed it a bit, and done some exploratory analysis to see what it looks like. So now we're actually going to get into modeling it. And so what I mean by modeling data is to to fit some kind of like statistical description of the data. And that might be described by a few parameters that we can adjust, and then use the data we have available to decide what those parameters should be, and then use those to predict new outcomes for unseen data. And so we're going to use a regression technique. It's known as Poisson regression. We're going to start from explaining what linear regression is. And I'm not going to get into any of these statistical depths of this, just a very high level approach to what regression is. And basically, linear regression solves the problem of, I have a load of data points, what is the best straight line I can fit through them? And so when we mean best, well, what do we mean by that? So what we do, we take a straight line, and this is going to be the line that we fit, and then we calculate the error between this line and all of the points here. So I guess, we take this line and can calculate, well, what's the distance vertically from this point to that? What's the distance vertically from this point to that? And we do that for all of the points. That gives us an error in our prediction for every single point. And then we take those errors and we square them. So that's got 2 advantages. For a start, it makes everything positive, which is a nice feature to have. Stops things from cancelling out. And 2, when we square something, it punishes large numbers more. So, let's think. Let's square the number 2, we get 4. So we've increased by 2 there. Let's square the number 8, we get 64. We've just increased by 56. So squaring things punishes big differences more. And that's kind of what we want. A few minor errors, not a big deal. 1 massive glaring error, that's a problem. So we square those, and then we now have a squared error for each point. And then we want to average all of those out. So take the mean of all those, add them all together, divide by how many there are. And that gives us what's called the mean squared error. And then the final thing we do is take the square root of that, and that gives us the root mean squared error. And that's kind of the metric that we're trying to optimize with this line. So there's various methods we can find this line. We can either use iteration, trying to improve this error all the time, or there's actually a formula to give us the correct one. But we don't have to worry about any of that. R handles it for us. Now, the problem with linear regression is that it's trying to model data that can take any value. So here, this line here, kind of, if we extrapolated this off to infinity, it would go into negative numbers. So because this x-axis is our input and the y is the predicted output. And it's kind of, our prediction is going to be positive it's going to be any value in this case. It could be positive or negative. But if we're trying to predict what the outcome of a football game is, well then that's not a very sensible distribution here, because football game scores, the number of goals you score are always positive. And also, they don't tend to have this kind of like infinite distribution in each direction. Like, there's a certain point you get to and then it's very hard to get more goals because of that fixed time limit in a game. And so we need a way of modelling the number of goals scored in a football game. And one way of doing this, it's not the only way, and it's there's a lot of ways to argue that it's actually oversimplified, is what's known as a Poisson distribution. So we're not going to get into the stats of that. Basically, a Poisson distribution is a statistical distribution used for modelling the number of things that happen in a fixed amount of time. And so it's got a single parameter, that's called lambda, and that kind of controls the average or expected amount of things you expect to happen. Am I not sharing my screen? I'm not, am I? I forget that it stopped sharing when I switch between. Okay, thank you for pointing that out. So the graph I was showing from above was this one here. And so, yeah, we calculate the errors between these points and the line, square them up, take the average, and that's our root mean squared error. So we're trying to find the best line through this data here. So then we get down to this Poisson distribution here. And so this is a good distribution for modelling how many times something happens in a fixed amount of time. For example, how many goals are scored in a football match. Now, obviously, a football match can be different lengths of time, could be like extra time. We're not going to worry about that. We'll assume it's 90 minutes. It's basically correct. And so, all we have to do is pick one parameter, and that's going to be called lambda. And that's the expected number of goals we would expect. And so, these are some kind of what Poisson distributions look like for when we expect to see 1 goal, 4 goals, or 10 goals. So let's say we expect to see 10 goals. Well, then the distribution of how many goals looks something like this. So the probability of having 10 goals is about 12%. Of having 5 goals, I don't know why I picked 10 as an example. It's very unlikely to happen in football. But then the probability of having like maybe 4 goals is 0.2, say, so 0.02. And that's the whole distribution. So you can see when lambda's small, when we expect very few, then it's the distribution centered around few goals, but as that increases, then we have this distribution over here. And so we can use a technique called Poisson regression to try and model this. So rather than with linear regression, we're modeling data that takes any values. With Poisson regression, we're modeling data that takes these kind of positive integer values. And so what we're going to try and do is from our data, is try and predict what the correct lambda is, so what the correct average value. So this could mean, for any given team, what is the expected number of goals we think they would score. But we'll have a few more things we're predicting. We'll get into that in a second. And so actually, there's a nuance to this. We're actually not trying to predict lambda itself. We're trying to predict the logarithm of lambda. And the reason for this is that even though we're trying to model positive data, it's more convenient to predict something that can take any value. And so this rate is always going to be positive. Like, we can't expect someone to score a negative amount of goals. And so this is always going to be positive. So we take the natural logarithm, so that's the ln function, because this takes strictly positive values and makes them go between minus infinity and plus infinity, if you took this really off kind of into the future. So that will kind of come in a second, why this natural logarithm matters, but just kind of hold that in your head for 1 second. And so actually, I'll explain a bit more about what we're actually trying to model. So the final model we're going to use is going to have 3 features. So I kind of mentioned there that we're going to try and model the expected number of goals for a certain team, but actually we're going to model 3 things. So in a given game, we're going to measure 3 things. So the first is who's one team, who is the other team, who's the opponent, and whether the kind of main team we're looking at is playing home or away. And so we'll have expected values for each of those. We'll have an expectation of how well does this team play. They'll have an expectation of, well, how much does the average number of goals change if we're playing against, team Y? And then also, what is the home and away advantage? So 3 things we're modelling in this scenario. Okay, so we can fit a Poisson regression model by using a function called GLM, which stands for Generalized Linear Model. So linear models, the straight line one. When we're modelling more complicated things like Poisson stuff, we use GLM for Generalized Linear Model. And so to do this, we pass in a formula where on the left-hand side, we have the thing we're trying to predict. We then have a tilde, one of these little squiggle symbols. On my keyboard, it's above the hashtag on the right. If you have a non-English keyboard, it might be in a different place. And then the predictors, the thing we're using to try and predict the outcome, are going to be on the right-hand side. And we separate those with a plus. And so then we set the family equal to Poisson link equals log. So basically a Poisson regression, and this kind of function we're using to transform the expected rate is the logarithm function. And then the final thing is we pass in the data we're going to train the model on as the data input. So an example might look something like this. So here I've made a data frame. It looks something like this. So there's a column called number of awards. Say this is a restaurant here. How many awards do they have? 7, 8, 3, 3. What is the price of a standard meal? 30, 35, 24, and 19. And are they in the city centre? False or true? And so what we're going to do, we're going to try and predict the number of awards by, so this tilde kind of means by, the meal price and whether or not it's city centre. So prediction on the thing that we're predicting on the left and the variables used for prediction on the right, separated by a plus. Then we do this family equals Poisson link equals log. Just we put that in every time we want to do Poisson regression. And finally, I call this data frame df here. So we made this and passed it into df. So my data is equal to df here. And when I run this, this is going to make a model, and I've saved that in this thing called model here. So I can have a look at the contents of this model by using summary on the model. So I run this here, and it gives me a lot of information. And if you're not kind of statistically trained, this is going to be a lot of kind of nonsense. But the one thing we care about is these estimates. Now these are the estimates of the effect of each input on the output. So we start with an incept here. This is kind of saying, so if we have kind of the default case, this is going to be a meal price of 0, and it's not in the city centre. What would we expect the number of awards to be? So yeah, it's an unrealistic point to start at, a meal price of 0, but whatever, we start from this. And then this says, for every increase in £1 of the meal price, how would we expect the number of awards to change? And this for the city centre is when we change to the city centre, what change we expect that to make to the number of awards. But the problem with this is that these are actually given, these show how the difference in the logarithm of the rate is going to change. So if we want to actually convert these into meaningful values, we have to take these. So I'm going to copy this here and use the exp function for exponential, so to the power of e, and put that number inside of it. So what this is saying is that for every time we increase the meal price by £1, we expect the number of awards to get roughly 1.08 times bigger. That actually seems way too big, but no, that could be reasonable. Yeah, that's probably because these are some massive changes here. So on average, adding an extra £1 increases the number of awards by about 1 and 0.08. Being in the city centre, so this seems negative here. It seems like being in the city centre is a bad thing. But once we take the exponential, we actually see this is actually a positive number. So this is saying being in the city centre gives you an advantage of kind of maybe 0.7 awards. And so the incept is saying that if we have a restaurant that charges you nothing and is not in the city centre, what's the expected number of awards going to be? It's about half an award. Now, obviously, we've extrapolated massively. This is not realistic because there are no restaurants that charge nothing. but kind of that's kind of what these things here mean. And so that's kind of what is mentioned here. One final thing we might want to do is that here we had this incept, and that's pretty useless. So what we can do instead is we can remove the incept by doing +0 at the end. That's saying don't give me an incept. So if I do this and this now, run this code again, and then look at the summary, we get rid of the incept, and now we have 2 of these for city centre false and city centre true. So now rather than saying what's the difference between making the city centre true compared to false, we now have their own baselines for being for false and being true. So this is kind of a more meaningful model, and we'll be doing this when we do things. But the key thing is, yeah, take these values here, put them in EXPS, and that gives us the expected change in the output for every changing unit of those inputs. Okay, so we need a way to evaluate how well our models are doing. And so to do this, we'll have to split our data into a training and a test set. So we'll use the training set to choose the right values of our model, the right coefficients, and then we'll predict on the test set. And the reason we do this is to make sure that we actually have modeled the data correctly, rather than just learning what the data looks like. You can imagine if I gave you 10 flashcards and asked you to memorize these, you could quite easily remember those and give perfect responses to those. But if I gave you, some more flashcards of different questions, you probably wouldn't be able to answer those because you haven't actually learnt anything, you just memorized things. And so the reason we use a train set and a test set, split out the learning and the evaluation of that, is to stop us from just remembering the data and not actually being able to predict new things. And so we can use a function called predict to predict the outcome for new variables, so for a new data set. And so for this, we pass in the first argument, the first input is the model itself, then the new data we want to predict for, and finally we add type equals response. And then we round this to get to a whole number. Well, we see an example of that in the breakout sessions. You'll see an example before you do your own one. And so so finally, we want to predict the output of... Oh, actually, sorry, missed a section there. So yeah, we want a way to measure the performance of the model. And so we're going to use this root mean squared error that we mentioned before. So take all the errors, square them, average them out, and do the square root. And the smaller that number, the better our model is doing. And so the final thing we're going to do is to predict the outcome for a hypothetical game. So to do this, we're going to need to predict the average number of goals, kind of the expected number of goals for each team, the home team and the away team. And those are going to be those rate parameters, those lambdas, in our Poisson distribution. But the nature of a statistical distribution is that just because we know the expected value, there's actually a whole distribution of what could happen. There's different probabilities of what could happen. So then what we're going to do, we're going to consider all possibilities, or kind of a subset of possibilities of kind of reasonable number of goals, and then use this function called dpois, which kind of says for a given outcome, what's the probability of that happening given a certain expected value. But we'll see that that's all coded up for you. You don't need to worry about the stats of that. And then finally, the last visualization is completely empty. That's all for you to do by yourself. And then once you've done that, you'll have your own, for your own teams, the expected outcome of the game. And so one final thing I want to mention is that our model is okay, but it's not great. There's a lot more that we could do. So we could include more years of data. Like we've used 3 years of data. We could include more leagues rather than just the Premier League. Now, obviously, this adds complexity. Like, teams change over time. We'd have to account for that. If we're using different leagues, then certain teams don't play each other. It gets kind of messy. But if you wanted to put some time in, that would be a sensible next step. Another thing to consider is that, are teams improving or regressing, getting worse over time? We're going to look at the home advantage, but we're going to assume the same home advantage for every team. Perhaps certain teams have more of a home advantage than another. That would be something to consider. And finally, there's actually a lot of data available, more than what we're using. We could use what players were playing in each game, who the referee was, various things like that. What day of the week was it played on? Maybe those affect the outcome. That's something to look into. And a final thing to look into if you really want to kind of can get into it is this thing called the Dixon-Coles model. And I'm going to pop this in the chat here. It'll be linked in the description of the recording. And this is kind of a more advanced model than the Poisson one that kind of handles low-scoring games a bit better. So there is a full multi-part R tutorial on this at the link I shared in the chat. If you're really into this, worth having a look. A word of warning though, it's quite old and the syntax of R has changed quite a bit since then. So it might seem a bit unfamiliar to what we're doing here, but all the code is there. Try and follow along with it and see what it's doing. And so the final thing to mention before we go back into breakout rooms, so it seems like we're unlikely to end by 5:30. And so hopefully a few of us will be able to stay on a bit longer, help you with any issues, or if you have to go at 5:30, get in touch with any of us. We'll be happy to kind of help you finish things off. So things to wrap up with. Follow us on Facebook, LinkedIn, and Instagram. We have loads more events, loads more workshops, kind of a lot of exciting things happening. Make sure you're aware of that. If you want to get more involved with the society itself, maybe taking part in talks, helping with our research perhaps, get involved with our community group. So if you go to this on Facebook, that's a smaller page where we kind of post more opportunities about what's going on in the society. We have posted some examples of how you can use Python for various different subjects, for kind of politics, for chemistry, for finance, whatever. Those are linked here. We're going to have some of those coming out for R fairly soon. Those will be posted on our Facebook and LinkedIn and Instagram once they're ready. And also check out our research blog if you want to know more about that. And the final thing, we're looking for both a marketing officer and a graphic designer. If you know anyone that would be interested, doesn't matter if they're that knowledgeable about data science. I mean, really all we want is someone that's passionate about graphic design or marketing, someone that can do their job well and help us grow more, reach more people, do more great stuff for the community. If you know someone that would be interested in that, please get in touch. Probably best either messaging me, LinkedIn or Facebook, or emailing hello@warwickdatascience.com. So with that, we'll move back into the breakout sessions. We won't join this call again after, and hopefully we can get this these templates finished, and you can have your own outcomes to kind of for your own teams. So thank you all for coming, and I'll see you in the breakout sessions.